Yes. Can you see my screen?
Yes.
Okay, thank you. My name is Zheng Zhao, and today I will represent TUDelft, present our method for the MagNet challenge. So first is our team members. This is the core team, me, Reza, and Regine, and we also have advisors who are also PhD students. And when we have problems, we can go to them. And we have supervisors, Zia and Mohammed. And then I'd like to move on to our method. To begin with, we proposed a seemingly very innovative method, and we name it as half machine learning, half equation method. So shortly speaking, we have a group of Steinmetz equation, and each equation is corresponding to a specific frequency range. And we add those Steinmetz equations calculated core loss together as the total core loss. And we want to use neural network to predict the Steinmetz equation coefficients. But we did some effort and we found out that this method has high accuracy for sine wave shapes, but it has poor accuracy for other wave shapes. So we gave up this method. And we also tried other AI method that is open sourced by the organizer. And by the way, thank you for your open source spirit so that we can quickly build our model based on your shared model. Yeah, but we tried them and we found they are actually very time consuming for training, especially on our own PC, and they are complicated. And so we proposed our own method, and it's very straightforward. And by the way, I really admire the previous presented methods. They are very innovative and very impressive. But our method is pretty straightforward, and we generally use first use FFT to decompose the B waveforms into harmonics with frequency and magnitude informations. So we input those harmonic information together with T to predict the power loss. And this is accurate and simple. And we have compared different input formats. For example, in this figure, we show that our harmonic information includes frequency and magnitude, but actually you can add the phase information. And also you can only input the magnitude of different harmonics, and you input only the fundamental frequency. And we compare different number of harmonics, 3, 5, and 10. And eventually we found out that with 3 harmonics and with only frequency and magnitude, in this way, the model has great accuracy and simple network structure. And then the next question is, can we enhance the relationship between the frequency and the magnitude? Because we know that the frequency and magnitude, they are linked with each other, but maybe the neural network didn't know. So we tried 2 different methods. The first one is we tried the partially connected input layer. So for example, for the first input and second input, which is only linked to the first and second neurons in the first middle layer, and so does the third and fourth neurons of third and fourth inputs. And also we tried another method is we use 1D convolutional neural network, where each pair of amplitude and frequency is treated as a 2-channel signal by the CNN. But we found out that with those methods, the accuracy is not increased. So we suspect that maybe the FMN already captured the boundary relationship between each harmonics. So we didn't continue with those methods. We remained the previous constructor. So we continue with the optimization because we realized that the evaluation criteria has 2 factors: the model accuracy and model size, and they are equally important. So I think this is a typical multi-objective optimization. And we think about the search space. We think about those variables: number of middle layers, number of neurons, activation functions, optimizers, batch size, and initialization method, learning rate scheduling. And as you can imagine, it will has a very big searching space. And if you want to optimize it completely, it will take a very long time. So we want to do a two-step optimization. The first one is we optimize those things that is mainly related to the network structure, and the second one is more related to the learning method. So the first one, we do it with Optuna, and here are the search space that we have defined. And you can generate these figures for each material. You can eventually get a Pareto front. And usually what you, and by the way, the x-axis is number of parameters, and the y-axis is validation loss, which means the accuracy. So usually you want to select your network parameters on the Pareto front. But then there is a question like how many number of parameters is good enough, and how low the average error is good enough. So we don't know, and we ask committee, and committee also doesn't know. So for example, if R2 has 1,000 number of parameters, and if you train completely, maybe say it has 1.5 average error, and R3 maybe have 2,500 number of parameters, and R3 has say 1% average error, which is better? We don't know. So basically we choose it based on our instinct. We choose the combination on the Pareto front near the knee point. So we think maybe near the knee point, the model has relatively low number of parameters and relatively low average error. And we did for other materials. And then we move on to the second step, optimization, and we define those search space. And after the optimization, the optimized parameters, with the optimized parameters, the accuracy is about the same compared to the tutorial learning rate scheduling and PyTorch default weight initialization method. So we think that maybe the original learning rate scheduling is good enough. So we didn't continue with this optimization. We keep the default numbers for those variables. And then we move on to the overall model training and comparison process, because the target is for the 5 new materials, and we already have 5 new material data, although they are relatively small compared to the 10 existing materials. So you can directly do the optimization and you train the model. And alternatively, you can do with transfer learning. So basically, you first do the multi-objective optimization for 10 existing materials. You train the model and you then do the transfer learning based on 5 different new materials. You get the transfer learned model. And here maybe you have a question. Why you train the base model based on the materials separately? Why don't you combine the materials together? So we did a small test and we try to combine the materials that we think they have similar properties. And we found out with the transfer learn result that the transfer learn result is not as good as if you only train the base model with only one material. So we think maybe new materials may show closer properties to a specific existing material rather than a collective representation of several. So we keep this format, and then we collect all the models, the transfer learned model and the self-trained model, and we compare them, and we see which is the best model. And here are some figures. So here is the transfer learned result. By the way, I saw the previous presentation from Fuzhou, which is very interesting, and I think they mentioned that N87 is the best, but here we found out that N27 and N30 may be better. I'm not sure. Maybe that's because of the model structure or the number of parameters difference. And I also noticed that if you train several times, the results could fluctuate a little bit. Maybe that's also related. But I think a general understanding is that maybe new materials show closer relationship with several specific material rather than other materials. So we also we marked the best model of the transfer learn results, and we also present the results without transfer learning. So we directly do the optimization, and we have the accuracy. So we compare the results with transfer learning and the results without transfer learning, and we see that although the results with transfer learning has a slightly higher number of parameters, but the average error is much better, especially for D. And in our test, it was about 10, but unfortunately, in our final test, it's much higher. That's a sad story, but yeah, we eventually submit our results with transfer learning. And that's the end of our story. And that's the end of my presentation. And if you have any further question, you can always contact us. You can contact Zan. And also now we can have a short discussion about our method.
Great. Thank you, Zhengzhao. Congratulations on a wonderful competition performance as well. Like you guys also did well across the materials, and the presentation was very good. Yeah. So I guess my question is, I really like the multi-object optimization strategy. And to answer your question about the accuracy, as we mentioned before, the accuracy will come from the measurements. So basically, in our opinion, if you know your measurement is 5% with 5% error, then maybe the goal is to train your model to reach 5% error, and then try to reduce the model size as much as possible. That's general answer. But again, to quantify the error is a difficult task. We don't know how to where the real ground truths are.
Yeah.
Yeah. Great.
Thank you.
Any questions, comments from the audience?
Yeah, I think overall this is a very good practice, and the result is also pretty good. So I also quite interested in the multi-objective optimization using the Optina. So when you're doing the optimization with Optina, did you train everything the same, for example, number of epochs? Because when I do this, I find this is sometimes quite time consuming to do a full training and then searching the results.
Yeah, that's true. So if I, for example, if I select one best combination, if I want to train completely, usually my experience is that it will take around 10,000 epochs. But if you do the multi-objective optimization, it's very time consuming. So what we said is for the 10 existing materials, for 200 trials and 1,000 epochs each maximum. So basically, I said this so that to give you a figure, for example, 3C90 material, we do the multi-objective optimization in my own PC. It takes 2 days. So that's some time that we can bear if it's if you can increase the number of epochs further, and you maybe have better results. But that time we couldn't afford to do it further.
Yeah, understand. And also another quick comment is like maybe if you want to further move on with this project, probably you wanted to in the searching space, maybe you want to split this optimizer and also batch size into the second stage, because in my experience, the optimizer and the batch size is closely related to the learning rate. So these two is kind of like a combined together, I think. And the first part will be mostly the structure related, like number of neurons layers, and then the second part is about the training, like the optimizer, batch size, and the learning rate, I think.
Thank you. That's a very good suggestion.
Yeah, great. Yeah, so I would say if you go back to your multi-object optimization, your team on the overall team sits right there. Like there are teams which offer better accuracy, but with larger model size, and there are teams which have better model size but lower accuracy. So you are sort of at the Pareto front in general.
Thank you.
Yeah. Okay. Great. So now let's move on to our final team. Indian Institute of Science. Our last team.
Yeah. Hello.
Hi, 你好。
Yeah, I will share my screen.